All right, now we know where the valence electrons are. Again, remember it's what group they're in. They are the ones that will form bonds, and they've got to do a couple different things, okay? They can form what they call an ionic bond, or they can form what they call a covalent bond. We're going to talk about ionic bonds now. What happens with ionic bonds is like you have a metal. Sodium has one on the outside. Okay, if it gives up that one, then it becomes stable because the next layer has 8 in it. So it's going to give up its one, and then it's going to give it to somebody that needs one. All right, that's an ionic bond where you transfer electrons. One gives it up, one takes it in, and it's called ionic because you form ions. Okay, and again, it's going to occur between those first two columns and those last 6, actually the last 5, because remember, the noble gases won't form any kind of compounds. But the magic number, the stable configuration, is 8. When they have 8, they're happy, except for hydrogen. Hydrogen only needs 2. Okay, that's all it's got room for. All right, so when we're drawing ionic bonds, what we're looking for is giving up electrons or taking in electrons, and taking in enough electrons to have 8, or giving up enough electrons to get rid of all of them on the outside, so then you go down to the next level and there's 8. Okay, and we went through I went through valence electrons in the last one. Again, remember the noble gases have 8, so they don't react with anything. Okay, all right, so we're going to look at ionic bond. We're going to make salt, sodium chloride. Okay, sodium has 11 electrons, but only one valence electron. It's in group 1. Okay, these are inner shell. All right, to achieve a noble gas, it has to lose this one. Okay, so if it's going to lose one electron, it's going to become a cation. It's going to become a positive charge. Okay, as of right now, sodium has 11 protons and 11 electrons. It's an atom. It doesn't have a charge. So what it's going to do is it's going to give up its one electron because there's only one on the outside. If it gives up that one electron, now its electron configuration is stable because it looks like a noble gas. That's what they're looking for, is to look like a noble gas. But because now it has one less electron, before it was 11, 11, now it's 11 and 10, that one extra electron, or losing that one electron, gives us a positive charge. So it's an ion. It's a cation. Okay? Chlorine is who it's going to give it to because we're making salt. All right, here's chlorine. Chlorine has 17 protons and 17 electrons. Its noble gas configuration, or its configuration, if you look, it has 7 valence electrons. It only needs one more, just one more. Come on, one more and I'll be stable. So it'll take that one from sodium, add it. Now it has 18. So it's stable because it's outside. If you look at its configuration, is the same as a noble gas. It has 8. 8 is great. Okay, so now chlorine is happy. But because, again, the protons don't change, but the electrons did, it took in one. So now it has 18 instead of 17. It has a -1 charge. So that's why it becomes an anion. Okay, so they work on getting their configurations. Like I said, this will be the configuration of the sodium ion, and make this a 6. This will be the configuration of the chlorine ion. Okay, so and the way they form a bond is sodium gives up one, chlorine takes in one. Now you have a positive one and a negative one. Okay, the charges are going to equal each other. Okay, so the sodium and the chlorine, if sodium transfers one electron to chlorine, they both become ions now. One becomes positive, one becomes negative. And then that way they achieve their noble gas configuration, because that's what they really want. They want to have the same configuration as the noble gases because they don't react with anybody. And again, they're looking for 8. Okay, but the attraction between the positive and negative is very strong. Okay, an ionic bond is a very strong bond. Okay, so that positive, oops, sorry guys, that positive charge between the sodium and the chlorine kind of holds them together. Okay, and so that positive and negative makes an ionic bond a very strong bond. Okay, they call that, or the ionic bond is formed because one gives up electrons. It's always going to be the metals that give up the electrons, and one takes in electrons. That's always going to be the nonmetals. Because remember, we talked about it when we were drawing these out. If you put a metal and a nonmetal together, they form ions. Remember, we had to worry about the charges and crisscrossing and all that. That's when it happens between a metal and a nonmetal. Okay. All right. In a solid state. So now we have salt. Okay. If you really get bored sometime, look at salt crystals. They all look the same. And that's because there's a very orderly fashion, the way they're arranged with the sodium ions and the chlorine ions. I know, who really has time to look at salt crystals, right? But anyway, they form this lattice. And the big ones are the green. The green are the chlorine, and the pinkish, I guess you'd call them, are the sodium. And they are attracted to each other because of the positive and negative charges. So they form a lattice. And all the salts, if you want to call them that, form a similar, they have their own kind of characteristic crystal form depending on the charges and where they form. Okay? So they stick together, they hang together because of their positive and negative charges. Okay? The cations are going to get smaller because they've given up a whole layer here. You know, they have one electron in this outside layer. They're going to give that up. So they lose a layer, so that's why they're smaller. And the chlorine is going to get larger because it gained one, and so it pulls it out farther. So it fills out this. So these get smaller. The metal ions get smaller, the cation, and the anions get larger, which makes sense because they're adding more electrons. Okay, so because the sodium is much smaller, it's going to actually have a greater attraction between its electrons and its the parent atom, in other words, the one it came from. Okay, so it's going to get attracted to it, and again, it's going to squeeze. The positive is going to be attracted to that negative. It's what keeps them together, I guess. Okay, the chlorine, because it's larger, is also going to have an attraction between its attraction is going to be less from the middle, from the nucleus, because it has more electrons. Okay, and so that's why it spreads out more. So the anions get larger, the cations get smaller, but makes sense too. The cations lose an electron, so they get smaller. The anions gain an electron, so they get larger. I guess it's easier probably to think of it as that way instead of in terms of what happens with the nucleus. Okay, and here's just showing you, you know, it goes from 1.52 to 0.06. It gets quite a bit smaller, and these guys get larger. Okay, so the metals get smaller when they become ions, and the anions, they get larger than the non-metals. Okay. All right. So when you have more than one electron, it doesn't just have to be one. Like calcium has 2 electrons in its outer energy. Well, if it gives away 1, it still has 1. So it's actually going to give up 2. And some of the nonmetals, like oxygen has 6. It needs 2. If you just give it 1, it'll be like, come on, I need 1 more. So it needs 2. So that's not just 1 transferred over to 1 and 1 takes it. Sometimes it's 2. Sometimes it's 3. 3 is pretty much it. Okay. 4 doesn't really happen. Then we're talking about covalent bonding. We'll talk about that later. So when you're talking about ionic bonding, it's going to be 1, 2, or 3 electrons are given up by somebody, and they're transferred over to a nonmetal that takes in 1, 2, or 3. Okay. All right. So like magnesium. Magnesium has 2. Its configuration, you know, it has 2 electrons in the outer energy level. And again, you don't have to think of the configuration if you just want to look it up on the chart. Okay. So it has 2. So to achieve its noble gas, it's got to get rid of those 2. Okay. Chlorine only needs 1. So if I'm going to make a compound between magnesium and chlorine, I'm going to need 2 chlorines, because the magnesium can give up 1 to 1 chlorine, but chlorine's done. I don't need any more. I'm full. So what I need 1 more chlorine. So sometimes, and remember when we did charges, if I did magnesium has a charge of +2. That means it has 2 electrons to give. Chlorine has a charge of -1. It only has 1 electron. So when I crisscross them, when I put a 2 by the chlorine, that's where it's coming from. Okay. I need 2 chlorine for every 1 magnesium. Okay. So when you're talking about that, did they show it? Yeah, here we go. So if you need to transfer more than 1 electron, that can happen. They can do that. Okay. So here we got magnesium. Magnesium's 12 protons and 12 electrons. Okay. It needs to get rid of 2. There's 2 on this outside, and there's no way it's going to find 6. So it's got to get rid of those 2. So what it does is, here's chlorine over here. Chlorine's looking for 1. Okay. So I'm going to give 1 to you, and I'm going to give 1 to you. All right. So I need 2 chlorine for every 1 magnesium. The formula is going to be MgCl2. Okay. So I'm going to have this magnesium is going to become +2 because it gives up 2 electrons. And the chlorine, each one of them individually is going to be -1. You have to make sure, if you look over here, we got +2 here, and we got a -1 and a -1. So we got -2 all together and +2 all together. Excuse me. They have to equal each other out. They have to, You know, if this is +4, +3 over here, this has to be -3 over here. They have to be the same. They have to equal each other out. Okay, so here's one where I transfer 2, but I needed 2 chlorine for every 1 magnesium because magnesium has 2 to give. Okay, so when you're doing ionic bonding, you have to make sure that the positives and the negatives equal each other. The charge on your cation and the charge of your anion, and there could be more than one, that when you add them up, they have to equal 0. Okay? Okay? So more than one electron can be transferred when you're forming ionic bonds. Aluminum, aluminum, it has 3 electrons to get rid of. Okay? So it could, if it formed a bond with chlorine, it would have 3 chlorines. Each one of them would be -1, and then aluminum would be +3. Okay, and that's the most. Aluminum, and let's see what's under aluminum. Actually, it's like boron and aluminum, about the only 2 that do that. Most of the time, those guys just, most of your ionic bonds are the ones that have 1 and 2, but aluminum will as well. Okay, okay, let's say I put aluminum with oxygen. Okay, oxygen has 2, aluminum has 3. Okay, so I can't just transfer 3 to oxygen because it can't take all of them in. So sometimes you gotta do a little configuring, all right? And honestly, the easiest way to figure out how many you need of each, write the chemical formula. So if I put aluminum has +3 and oxygen has -2. If I crisscross them, I get Al2O3. I'm going to need 2 aluminum and I'm going to need 3 oxygen. And that happens, okay? So 6 electrons need to be transferred, 3 from 2 aluminum, and then I need another aluminum, you know, because I'm going to transfer 6, 2 to each of the oxygens. I hope I have that. Yeah, here we go. So aluminum has 3. Why are we doing fluorine here? What happened to my oxygen? Anyway, if I was just doing fluorine, it would be easy because I could put 1 here, 1 here, 1 here. Then I'd have -1, -1, -1. Okay, but if I had oxygen, oxygen has 6. So if I take these 2 and give it to the oxygen, I still have 1 left over. So then I have to add another oxygen. And I give it 1, and then it's like, oh, wait a minute, this oxygen needs another one. So if I was doing aluminum and oxygen, I'd have 2 aluminum and 3 oxygen. And again, just write the formula, and then you'll figure that out. But you need to transfer the electrons over, and now they have a new charge. When you write out ionic bonds, it's important that you put the charges in, okay? All right, so in almost all stable compounds, your main groups, and when I say main groups, that's the S's and the P's, they're looking to maintain, or they're looking to get to a noble gas configuration. In other words, they're looking for 8. Okay, metals lose electrons, non-metals gain electrons. It's pretty much that simple. Okay, so if you want to predict the ionic formula, you guys, you can just write it like we did before using your ion chart. So if I'm going to do between, let's see, calcium and oxygen. Calcium is +2, oxygen's -2. CaO. Calcium's going to transfer 2 to oxygen. Okay. If I'm doing between magnesium and phosphorus, okay, phosphorus is 3, magnesium's 2. So I'm going to need 3 magnesium for every 2 phosphorus. Write the formulas and then you'll know how many you need. Okay. Here's barium and sulfur. Barium's +2, sulfur's -2. So it's going to be BAS. I'm going to need 1 barium and 1 sulfur. Okay? +2, -2. And so I need 1 barium, 1. The barium's going to take into, or give 2 to sulfur. Barium's going to become +2, sulfur's going to become -2. And that charge table that I gave you, that's the charges that they'll form when they form a compound, an ionic compound. Okay? Here's some more lithium. You can see the oxides and everything. But because they have the same group, similar valence, they're going to typically have the same formula. Okay? Trying to see. All right, potassium phosphate. Potassium is 1, phosphide is 3, so it'd be K3PO4. I mean K3P. I'm doing my polyatomic ion, sorry. Right there. And again, it's just your crisscrossing. Sodium is Na, it's 1, sulfur is 2, so Na2S. Okay, I'm hoping we're getting, I'm trying to look here. Okay, so we're good. All right, we'll pick up on covalent.